slides with you. Before that, let me stop this. Okay. Okay, now you should be able to see the slides. We are going to talk about tree trees. In tree, actually, it's not a binary tree. So true is for binary nodes. So some nodes are binary. True has two subtrees, and one data piece is stored over here at the parent. But some nodes show two data piece and has three subtrees. For example, if this is X and this is Y, everything is X is less than Y actually, and everything less than X will be in this subtree, less than X, and everything greater than X but less than Y is in the subtree. Everything greater than Y will be on this subtree. Okay, it is similar to binary search tree, but we store two elements sometimes in a node in true tree. That's why it is not a binary search tree. Actually, tree is a special case for B trees, where we have at most two data pieces in a node. We are going to see the generalization of this kind of trees as B tree later on. We have two types of nodes. Two nodes has one data element is stored and it has two children, and three nodes stores two data elements and has three children. So we may have two nodes or three nodes. And one more condition in tree, all leaves are at the lowest level. So it is balanced. So this is a tree. When you look at the leaves, all are at the same level and lowest level. Okay, as you see, some of the nodes are true nodes. This is a true node. This is a true node. Some of the nodes are three nodes. This is a three node. This is a three node, right? So two pieces of elements. Okay. Another thing here is we again when we insert the elements at the leaves only in this tree, and we are gonna see that trees, regular binary search trees, grows top down, but this tree will grow bottom up. We are gonna see how it happens in a minute. What about the search operation? Insertion and deletion will be talked later on, but what about the search operation? Again, the search starts from the root. If the root is true node, we compare the search key with 7. If it is smaller, we continue with the left subtree. If it is larger, we continue with the right subtree. Let's say we are searching for 14. 14 is greater than 7, so we have to continue with the right subtree. Then we come to this 3 node. In 3 node, we have 2 pieces of elements, and we compare the key 14 with 11. It is larger, so we do not traverse this, since it contains the smaller elements. We compare with 15, it is smaller, so 14 is greater than 11, less than 15, so we have to search this subtree, not this one, right? When we come to this node, this true node, we compare 14 with 13. We have to continue with the right subtree, as in binary search tree. But right subtree is empty, so we can say that 14 is not available in this tree, right? So it is very similar to binary search tree. Actually, when we have two nodes, it is completely the same. But when we have three nodes, we have to be careful since we have two stopping case when the item is equal to the first data field or second data field, we stop. Of course, if it is less than the first data field, we recursively continue with the last subtree. If it is not less than data field 1, but less than data field 2, we have to continue with the middle subtree. Otherwise, it is larger than both data fields, so we continue with the right subtree. In the three node case, true node case is same as the binary search tree. Okay, searching is simple. So at each node, we compare one element or two elements and continue with one of the subtrees. So the search performance depends on the height of the tree. And the height of the tree is between log 2n and log 3n. So height is between these two values, -1, +1, small differences, as we are going to see later on. But all in all, since the height is logarithmic and the running time depends on the height, the search operations running time will be logarithmic. Okay, this algorithm takes O log n time, since the best case is finding the element at the root, constant time. Worst case is finding at the leaf, which is logarithmic time, so the running time will be O log n. Okay, for example, when we search for 13, we start with 7, it is greater, so we compare 13 with 11 and 15. It's between these two numbers, so we continue with the middle child. We compare 13 with 13 and we found it. Okay, it is very similar to binary search tree actually, except this three node requires two comparisons. When we talk about insertion, remember, we always insert as a new node in binary search tree, red black tree, or AVL tree. But in 233, we insert add a leaf. We do not create a new node, but insert directly into a leaf. For example, if we have to insert 6, it should be on the left of 7, right of 3. So we insert 6 right away here and make this node to be 3 nodes. Okay, so we always insert into a leaf. For example, if we have to insert 10, it is greater than 7, less than 11, greater than 9, so it's leaf, so we insert 10 over here. But if we have to insert 20, 20 is greater than 7, greater than 15, and we insert right here. But now we have 3 elements here. What we are gonna do? In this case, we split this node and move the middle element into upper level. This split and move operation would propagate until the root, actually. And when the root is splitted, tree height will increase, of course. So the height will increase bottom up, not top down. That is what I have said before. The tree grows bottom up, not top down, as in binary search tree. So tree is built from bottom up, not top down. We do not insert a new node as a leaf, but we insert the element as a new element into a leaf. Okay. For example, when we have to insert 15 into this 233, 15 is inserted to the right of 7 in this, besides this 11, so it becomes 3 nodes. And we have to insert 17 again. Right now, 17 should be inserted on the right of 7. And so in this leaf, but when we insert, it should become 4 nodes. There's nothing like 4 nodes. So we cannot store 3 elements in a node. So we split this node as 1 node this one node this one, and move the middle element to upper level. So the upper level will be 7 and 15, and everything less than 7 is 3 here. Everything between 7 and 15 contains 11 and this 1 node, 2 node actually, and everything greater than 15 will be here, and it is this true, whatever contains in this true node, 17. So we are gonna have this 233 after split operation. It is perfectly fine, 233, as you see. We can continue insertions. We can insert 5, then 10, then 20 without any split operations. But if we insert 13, 13 is between 7 and 15, so it will be inserted in this node. Not insert one more value in 3 nodes. So we have to split and move the middle element to upper level. Something like this actually. But this upper level cannot contain 11, which is, it used to be 3 nodes. It cannot contain one more element. So it should split. That the root should split as well. So the middle element will go up, one level up. So here, since it is the root, we create a new node and split the 7 and 15 as 2 1 nodes. Okay, becomes like this. As you see, the tree grows bottom up. Leaves stays as they are, but it grows bottom up. In regular binary search tree, root stays as the root and tree grows top down. Right? So this is the insertion algorithm. This is very similar to insertion algorithm of binary search tree. This part is very similar, but we have to make some corrections after insertion. If there is a split, we have to correct it here and here, actually. If the root is null, empty tree, and we create a 2 node and create a 1 node tree, this is a special case. If we found the item at the root, so we cannot insert once more, so we return false. These are special cases for binary search tree and AVL tree and red black tree, etc. for all of them. Otherwise, if we hit through a leaf, we have to insert over there. Of course, when we hit through a leaf, we insert into, if we insert into a 2 node, it becomes 3 node and the value is inserted and we are done. If the leaf is 3 node, not 2 node, but 3 node, in this case, we cannot insert one more element. So we have to create another node. Actually, we had a 3 node with 2 elements, X and Y. We create two nodes, put the left element here, for example, X, and the new element comes to middle, let's say. We put Y here. The new element, this will be new parent, will be pushed upwards, so propagate to parent. So N should be passed to parent as a new element. New parent back up to the recursion chain. So N will be handled by the parent. If a new element is larger than the both elements, then N will be here and Y will be propagated back to parent. Okay. This part is for recursive calls. If the item is smaller than the smaller item at the local root, we continue with the left child and recursively insert into the left child. if it is true node and greater, we continue with the right child. If it is three nodes and less than the larger item, we continue with the middle child, or we continue with the right child. So these are recursive calls. After recursive calls, we may get a new parent. If the new parent was passed from this recursive calls, actually only one recursive call is made, not more than that, from previous level of recursion. If there's a new node, then we have to handle it. We have a new parent, and we have to include that parent into the current node. If it is one node, we can easily insert it by making it three nodes. But if it is three node, then we have to split that node as well. Right? And if the current node is the root, then we have to perform special operation. We create a true node as the parent and insert the middle element here and create two true nodes to make this thing, right? Left child and right child. Okay. So having that node as a root is a special case that is handled by creating the parent. If it is not, we insert the new parent into local root by either splitting or um, or making two node to be three nodes. Okay. So what we do actually is first going down to a leaf to find insertion position, then go up until the root to perform splits or not, right? So the running time will depend on the height of the tree as well. The height is logarithmic, as I said, so it is still logarithmic time for insertion as well. If we have to insert these, the words of this sentence one by one, first we create a one node tree for V, and when we have to insert quick, it is going to be inserted at the same nodes, since we make the root from true node to three nodes and insert quick. When we have to insert another one, we cannot insert brown, and what we need to do is to split and move this brown to the parent. Since it is a root, we create a two nodes and split to get this 2, 3 node, 2, 3, 3. And when we insert fox, it is greater than brown, and it is inserted in the leaf with quick. When we insert jumps, it is greater than brown, it is inserted with fox and quick, but right now it is 3 elements, so it should split up. Jumps will be moved to the parent. After split operation, we have this one. And over is greater than jumps, so it's inserted with quick. The is greater than jumps, it is inserted. And we have to split this node again. Quick will be moved to parent. And when we have to do this, the parent is overloaded. So jumps will be moved back to its parent, but it's root. So we split and make a new node for jumps as root. And we continue insertion, and we are done. This is a perfectly fine 233. We can insert more elements to the leaves and internal nodes as leaves gets full, but still it has height 3, and for each search and insertion we have to perform we have to traverse 3 nodes in this tree. In this tree we have to traverse 3 nodes. Okay. As I said, the number of nodes depends on the whether the nodes are 3 nodes or 2 nodes. If all the nodes are 2 nodes, the maximum number of nodes is this big. And if all the nodes are 3 nodes, the number of nodes is this big. So n should be in between 2 to the h minus 1 to 3 to the h minus 1. So to the h less than or equal to n plus 1 to the h, right? So when you take the logarithm, n plus 1 should be greater than log 2h. H is less than or equal to log 2n plus 1. And when you look at here, h is greater than log 3n plus 1. So h is greater than or equal to log 3n plus 1. So height is between log 2 and log 3n, or n plus 1, doesn't matter. So the height is logarithmic, is between log 2n to log 3n. So the search time is logarithmic, insertion time is logarithmic. When we come to removal, we perform almost reverse of insertion process. We delete the element. If it is deleted from the leaf, we simply delete it. If it is not from the leaf, we swap it. It is in order predecessor or in order successor. Here we use predecessor as the convention. So we try to delete from the leaf always. So deleting from leaf can cause an empty leaf. We do not allow empty nodes. If that's the case, we combine with its sibling and redistribute the elements. And sometimes we have to combine with its parent as well. So if we have to delete 13, for example, and we delete 13, this node becomes empty. And we have to combine this node with one of its sibling, either left sibling or right sibling. We can prefer one of them. Here, we prefer to merge with right sibling. So 15, 17, and 19 are merged together. And of course, there are 3 elements. So one of them moves up with split operation. If we have merged this with 9, of course with 11 as well, in that case, this tree becomes 15, 9 and 11, and 17 or 19, right? That's also possible. It is a choice. You can merge with last sibling or right sibling. Of course, while merging, you have to consider the element at the parent as well. Okay. So if we remove 11, 11 is in the internal node, not a leaf. So we have to replace it with the in-order predecessor. In-order predecessor is 9. So 9 will come to this position and this node becomes empty. And in that case, we have an empty leaf. We have an empty leaf here. This empty leaf has to be processed, merged with 15, and 9 and 15 are 2 elements. So it will become 17, 9, 15, and 19, right? As in here. Okay. So if we have, for example, if we have to delete 1, then we have to merge this the sibling with its parent. So it becomes like this. Now this becomes empty. So we have to merge these 2 with parent, and it becomes like this. So the height of the tree is decreased by this operation. For example, if we have to delete 7, in this case, we have to replace 7 with its predecessor 5. So 5 comes to this position. This becomes empty. So we merge these together. So if it becomes 1 and 3, and this becomes empty. So we merge these with its parent. So what we have is 5 and 17 at the root, 1 and 3 over here, of course in middle 9 and 15, and at the right 19, right? This would be the resulting 233 after removal of 7. Okay. So removal still requires to find the node, which takes logarithmic time, and we propagate the combine operations until the root. So it is logarithmic time. So the total running time will be logarithmic for removal operation as well. Okay. So all these insert, delete, and search operations are all log n operations. Okay. For 233. Now we are going to talk about B trees. B trees is the generalization of 233s. In 233, we have two nodes which has just one element, and three nodes which includes three elements and two elements and three children. In B3, we generalize this, and we have a maximum number of elements and minimum number of elements that can be stored in a node. So if the maximum number of elements is 100 in a node, the minimum number of elements is 50. Actually, we will talk about not the number of elements, but number of children, as in here. This is 3 node. This is 2 node, right? Based on the number of subtrees. The number of subtrees could be as large as, for example, 100, and as little as 50, let's say. So the number of data could be 99 to 49 in this case. What do we do that? Why do we do that? Because in hard disk or secondary disks, any secondary disk, is organized as blocks. And when you read a block, you would like to use that block completely. And you can store several elements in a block. So you design the number of leaves and number of children, number of subtrees as the block size. By using the block size, you store as many as no children in a block. So, for example, here we have 5 children in a node as most, and we may have 4 children here, 3 children here, 3 children here. 3 is the smallest value, 5 is the largest value. Okay, we call this value as the order. In this case, the order is 5, right? So each node can have order number of children, or order over 2 number of children, or in between these two. Of course, number of data elements is one less than the number of child. So each node should have the number of children in between this true value. There is only one exception for the root. Root may have last child. Even one child is possible. Not one child, of course. Two children is possible for the root node. Okay. Data elements are stored in increasing order. So everything is less than 10 will be here. Everything between 10 and 22 is here, etc. Everything larger than 40 is in here, in a sense. I'm not gonna go further since our time is up. We are gonna stop here and continue about B-trees next week. Next week we are gonna talk about B-trees and skip lists and complete the talk about these balanced binary search trees. Okay, balanced trees. Okay, I will stop here. Remember, tomorrow we have an exam. Please be there before 15 minutes, 20 minutes before the exam date for ID check and paper check, and be ready for the exam. Okay, do you have any question about the topics today?